Hello, ma'am. Good evening. Uh, okay. Hmm. Okay. So, let's wait maybe couple more minutes so that if anybody wants to join, they can join, and then we'll start. In the meanwhile, if you have any doubts that you want to ask, you can ask.
So what are the topics that we will be discussing today?
Okay, so there will be few problems related to uh, Clebsch-Gordon coefficients. I think two of them. Yes. One problem will be the Wigner-Eckart theorem, and then there will be several problems regarding addition of angular momentum, and I think two problems related to tensors and vector components. Okay, so the tensorial operators.
For tensorial operators, which book would you recommend?
Hello, ma'am. Sorry.
For tensor operators, which book would you recommend?
So I followed Sakurai. For tensor operators, I think J.J. Sakurai describes it nicely.
Your words of breaking. One is J.K. Sakurai and the other one is
I know it's J.J. Sakurai. So J.J. Sakurai. Okay, I have the book here. Yes, I think I have the fourth edition. So let me show it. No, third edition. This one. Can you see it? It's Modern Quantum Mechanics, J.J. Sakurai, third edition.
there is another book by Shiv.
By?
There is some voice issue. Ma'am told one more book on tensor, quantum mechanics by Shiv.
Schiff is also there, yes. But to be honest, I didn't read Schiff, so I cannot give you a good review or feedback on Schiff. So I followed Sakurai mostly.
Okay. And if you compare Sakurai with Zetli,
So Zetli is a little easy to follow compared to Sakurai. If you are having difficulties follow Sakurai, then I would suggest that you go through Zetli. Zetli, Zetli also have a lot of solved examples,
mm-hmm.
so those are also very helpful.
But it covers everything. Huh? Zetli also covers everything.
Yes, mostly. It has a separate chapter for angular momentum. So yeah, it and Clebsch-Gordon coefficients, everything is there.
If I want to study about complex potential from non-Hermitian matrices, okay, non-Hermitian operators, is there.
Mm-hmm.
Non-Hermitian operators, non-Hermitian Hamiltonian,
Okay.
then any reference for that?
Uh, okay. Let me quickly check. So the books that I have, they don't. I can't see any chapters based on this thing. I think, but there will be some separate books. I'm sure. Let me quickly Google. Yeah. So for example, there is this book called Non-Hermitian Quantum Mechanics by Nimrod Moseyev. So because this is this non-Hermitian quantum mechanics, this is very advanced, right? And it's very kind of a specialized topic. So it won't be there in general quantum mechanics books, right?
Okay.
So then you have to follow some specialized book.
Okay.
And they are there. I can see 2 3 books
Mm-hmm.
that you can follow along the lines that you are talking about. So I think those can be helpful.
Okay.
Yeah.
Okay.
Okay. So should we start?
Yes.
Okay. Great. So this is tutorial 11, second last tutorial. I think I'll also take one extra tutorial at the end. Anyway, so this is more like a warm up problem. So easy first problem. And okay. So what are we given? We are given that the ground state energy of hydrogen atom E1 is minus R, where R is the Rydberg constant, 13.6 eV. If the atom makes a transition from the excited state n is equals to 3 to the state n is equals to 2, then the radiation emitted would be this much eV. Okay, so we have n is equals to 1, n is equals to 2, n is equals to 3, right? And the energy for the ground state is given as 13.6 eV, and the transition is happening from n is equals to 3 to n is equals to 2. So this will emit a photon, right? This will emit a photon, and we are asked about its energy, h nu. Okay, so this is the problem, right? So we know that for hydrogen atom, the energy, okay, for hydrogen atom, the so the energy dependence is, we know it is 1 by n square, right? So the constant of proportionality is minus r, right? So that when n is 1, for n is 1, we get E is equals to minus r, which is also given here, right? So that's it. Now we have to check for n is equals to 2 and n is equals to 3. So for n is equals to 2, our energy will be minus r over 4, and for n is equals to 3, our energy will be minus r over 9. Okay, so what is r? R is 13.6, so this will be minus 13.6 over 4, which is minus 3.4 eV, and this will be minus 13.6 over 9, which will come out to be roughly 1.511 eV. So the energy delta E will be E3 minus E2 that will be minus 1.511 minus of minus 3.4, and this will come out to be 1.89 EV.
So
Yes.
transition E3 to E2 means shouldn't it be E2 minus E3?
Shouldn't it be E2 minus E3? Yeah, but okay, you can take E2 minus E3, doesn't matter, because we are calculating delta E, which is the difference. And
Okay,
because you can see the E3 energy is higher, that is, it is less negative, so that's why I have written E3 first. Right? We just want the difference of these energies, so this is delta E, right?
right.
Yes. So E3 is more, E2 is less. That's why I have written E3 minus E2. Such that so that the difference comes out to be positive, right? Because we just want the difference between these two levels, delta E, and it is coming out to be 1.89 EV. Okay. Yeah. Okay. So now let's go to some angular momentum problems. Right. So this is also fairly simple one, and what it says that we have we have to add two particles and their angular momentum are given. So J1 is this much and J2 is this much. Okay, so we have J1 as 5 over 2 and J2 as 3 over 2. Okay, and so to add to add two angular momenta, we use triangle inequality, right? Triangle inequality, which is mod of J1 minus J2 should be less than equals to J, which should be less than equals to J1 plus J2. Okay, so this is the lower bound and this is the upper bound. So our J, the total angular momentum, so this J is the total angular momentum. Okay, and it is bound between these two values, so J1 minus J2 mod and J1 plus J2. So let us find out the lower bound. So J1 is 5 by 2 and J2 is 3 by 2. So this will be mod of 5 by 2 minus 3 by 2, which is nothing but 1. And for upper bound, it will be 5 by 2 plus 3 by 2, which is 8 over 2, which is 4. Okay, so our J is restricted between 1 and 4. So the possible values of J will be J is 1 and then we always add plus 1, so it will be 2, 3 and 4. These are the possible values of J, which means option C. Okay, any doubts in this one?
Okay.
Okay, good. So just remember that this inequality gives us the bounds of our J. Okay, so moving forward. Now this problem. So here we are given that the matrix element of Z between 4f and 4d hydrogen atom is given by this quantity. So this is given to us, okay, where a0 is the bore radius, and then they are asking, so if this is given to you, then what will be this value? Where notice that what have changed. So here m has gone from 2 to 3 on the left side, right, on the bra side, and z has changed to y. These two things have changed. Now to solve this thing, okay, does this look somewhat familiar? Like, what should we do? Do you want to take a guess? How how should we proceed on solving this? Okay. Anyway, so okay. So first of all, what is this z and y, right? So these z and y are the components of position vector, right? And okay, let me write z y are components of position vector r, right? And this r is a rank 1 spherical tensor, right? Rank 1 spherical tensor. Okay, so our z is defined as t0, and this 1 means the rank, and our y is defined as iota by root 2 t1 plus t minus 1. Okay, similarly our x is defined as iota by root 2 t1 minus t minus 1. Okay, but for this problem we will not be requiring x, we just need z and y, so I'll just remove this thing. Okay, now most importantly, the theorem, the Wigner-Eckart theorem. So what is the theorem? Theorem is L comma m tq k L prime m prime. So this we can write, okay, 1 second. So this we can write as L prime k m prime q L m, and then this thing. So we have a fraction here, we have L tk L prime, and then under root 12 plus 1. Okay, so this is the theorem. Now if we look at what is given to us, so this thing is given to us, right? 4f m is equals to 2 z. Let us write it down. What is given to us is 4f, sorry, capital F, 4f m is equals to 2 z, 4d m is equals to 2. This is given to us as minus root 2 by 3 a naught, like this. Yeah. Okay, so now also we see that this z we can write as t01, right? So this z is t01. Okay, and the next thing, that for 4f and 4d states, so what will be the value of L here? So our angular momentum L will be how much for an f orbital?
3,
3. And for d,
2.
2. So here L is 2. Right. So if we now compare with this thing, so here we have L is 3, M is 2, right? And then this, instead of TQK we have T01, and L prime M prime we have 2 comma 2. Correct? So we can now write this as 3 comma 2 T01 2 comma 2. Okay, and then the right hand side of our WE theorem, the right hand side will give us, so this L prime is 2, K is 1, so 2 comma 1, and then M prime is 2, Q is 0, right, and then 3 comma 2. Okay, so these are the CG coefficients, right, the Clebsch-Gordon coefficients, and then this will be multiplied with this thing, which is nothing but 3 T12, L is 3, T1, L prime is 2, divide by, and L is 3, so 2 times 3 is 6 and 1 is 7, so divide by root 7. Okay, and we also know that this thing is equals to minus 2 by root 3 a naught. Okay, so this is equals to minus under root 2 by 3 a naught, right? Now the Clebsch-Gordon coefficient of this thing, so this Clebsch-Gordon coefficient is 1 by root 3. So therefore what we have? We have 1 over root 3, 3 T1, 2 divided by root 7, and then this is equals to minus 2 by root 3 a naught. So this root 3 will cancel out, and what this will imply is that this 3 T1 2 divided by root 7 is just minus under root 2 a naught. So we have calculated this value. Let me add a page. Okay. Okay, so going back, this was, let's just review what we have did. So this was given to us, okay, and we need to find this. So using the thing that was given to us, what we did, we compared this with Wigner-Eckart theorem, and now Wigner-Eckart theorem has two factors. One is the CG coefficient and other is this term. So to find out this term, we use this relation. This value was given to us, So now we are able to find out what this term is, because this exact same term will be required when we find out this quantity. So now we'll apply this Wigner-Eckardt theorem to this second quantity. So what do we have now? So for y, we are asked to find out this value. For f, m is 3, y 4d, and m is 2. We are asked to find this out. Now we know that y can be written as this thing, iota by this iota by root 2 t1 plus t minus 1. Okay, so iota by root 2 t1 plus t minus 1. Okay, so when we apply the Wigner-Eckardt theorem to this thing, it will have two terms, right? So now again, because this is f, so this thing will become, so corresponding L will be 3, and here corresponding L will be 2. So this will become 3 comma 3 y 2 comma 2, and this we can write as, so we will take iota by root 2 outside, and this will have then two terms. So one will be 3 comma 3 t1 2 comma 2, and other term 3 comma 3 t minus 1 2 comma 2. So these two terms. Now if you look here, so here we have this m prime and q. So this is our theorem. Let me take it down. Okay, now by selection rule, so what is our selection rule? Selection rule is that we need to have m as m prime plus q, right? So this is m, this is m prime, and this is q. So this is our selection rule. So if we apply this selection rule, so we see that for the second term where we have this minus 1, right? So q is minus 1, so m prime plus q will be, so this will be m, so here m prime is 2 and this is minus 1, so this will give us 1, and m is 3. So because 3 is not equals to 2 minus 1, so the Clebsch-Gordon coefficient of this term will be 0. So this term will give us nothing. For this term, however, you can see q is plus 1, so 2 plus 1 is 3, and this is the maximum weight state, right? So its Clebsch-Gordon coefficient will be 1. So we can write this first term as iota by root 2, okay, and then this thing. So here L prime is,
Sir, is y 1 or iota over there?
sorry,
Y equal to 1 by root 2 t1 of 1 plus t minus 1 of 1. Is it iota by root 2 or 1
it
by
is
root 2?
iota, it is iota.
Okay.
Okay. Okay. Right. So here L prime is 2, k is 1, and m prime is 2, q is 1, and this thing with 3 comma 3. And what will be this thing? So here L is 3, here L is 3, and this is T1, and then L prime is 2 divided by, again L is 3, so this will be under root 7. Now if you look here, this quantity we have already calculated, so this 3t2 by root 7, 3t2 by root 7, and we know that this comes out to be minus under root 2 a naught. Okay, so this value we know is minus under root 2 a naught. Okay, and this we know the Cliff's Gordon coefficient, that this is 1 because this is the highest maximum weight state. Therefore this quantity 33y22 33y22 is simply iota by root 2 into 1 into minus root 2 a naught. So this root 2 will cancel out, and what we'll have is minus iota a naught. That's it. So this is our final answer. Okay, so this was a little lengthy problem. So let me quickly recap what we have done. Okay. Okay, so the question says that we have two matrix element. So one is bit of matrix element of Z that is given to us, and we are asked to find the matrix element of Y. And notice that we are always between 4f and 4d states of hydrogen. So because we are in the same state, so this second term in the Wigner-Eckart theorem, basically this term, you can say it only has L dependence, right? There is no M. So we have L, L prime and L. And here if you compare these two, this one and this one, here also we have L as 3, L as 3, and here L is 2, L is 2, right? So our L prime and L are same in both the cases. So essentially, using the Wigner-Eckart theorem, this factor is same, right? This factor is same for both these elements, matrix elements. So only thing that will change, because this Z has changed to Y, so only things that will change is the CG coefficient. So these values. Okay. So for the first case, for this case, the CG value is coming out to be minus 1 by root 3, which allowed us to find the value of this term. And then once we know this term and know the CG coefficients for the second case, then we can basically tell the value of the entire thing, right? The matrix element of Y. Any doubts?
I have one doubt.
Yes, please.
You wrote L dash K comma M dash Q L M.
Where? Here?
Yes, in the Wigner-Eckart theorem.
Yes.
So L dash K means are we multiplying the values L dash that is 2 and K value 1, or are we writing them?
There will be a comma here, like this. So this is like this. So here, for example, you see I have written 2 comma 1 and then 2 comma 0.
Okay,
So
that
we
was
are not multiplying. I missed a comma here. Sorry.
that one is there, and another one, the Klebs Gordon coefficient. You got them to be one of Klebs Gordon coefficient 2 comma 1 semicolon 2 comma 0 3 comma 2. Its value is 1 by root 3. You
Yes.
wrote that. Could I see the step of? how we got that.
So for this one, I didn't explicitly calculate. However, in principle, one can calculate. I just looked up the value. So there is a table of Clebsch-Gordon coefficients from which you can find out the value of these Clebsch-Gordon coefficients. If you know, so if you know this thing, right, that your L prime M prime is this. Sorry, if your L and M are 3 2, and your L prime M prime K Q are this thing, then you can look up the table and find the value. However, in principle, we can also calculate. For this problem, I didn't calculate. Okay.
Okay.
So
Oh,
later on, okay, I had planned to give one small tutorial, like one example of calculating the Clebsch-Gordon coefficients manually, because these values are little high, no, 3 2. So this would take little long time. So just for the sake of time, I just use the values directly. So for this problem, I wanted to emphasize how we can use the Wigner-Eckart theorem, right? And yeah, you are correct that I have simply used that this value of Clebsch-Gordon coefficient is 1 by root 3. But I'll do a separate like problem to show you how you can calculate any Clebsch-Gordon coefficients. Okay, then you can
right.
find this on your own.
Okay. That's hard. So could
Yes,
you scroll down a bit?
yes.
Afterwards, what we will just click on the thing.
Sorry.
Um, okay.
Yeah.
Yes. Um, Selection rule M equal to M dash plus Q.
Yes. So this is the selection rule. If this if this rule is violated, then we can directly say that our Clebsch-Gordon coefficient will be 0.
Okay.
Okay. So there is a proof of this selection rule, and it is given in Sakurai. If you are interested, you can look up that proof. But by using the selection rule, we can we can eliminate a lot of Clebsch-Gordon coefficients. Okay. Okay. Any other doubts?
Um, no,
No. Okay.
but
Yeah.
sir, wait, you wrote 3 not equal to 2 minus 1.
Yes. So here, if you compare, okay, compare this second term. So I was talking about this one. So here, if you compare, what is the value of Q? Compare this with this. Okay, compare both. So here you can see the Q is minus 1,
Yes.
right? And this M prime is 2.
Yes.
So this M prime plus Q will be 2 minus 1,
Yes.
which will not be equal to 3, which is M. And on comparison, you can see this M is 3, right?
Yes.
So that's
So,
why this rule is violated. So the Clebsch-Gordon coefficient, so this term basically, this term will go to 0 for this case. So this entire thing is 0, right? So this entire thing is 0.
okay, sir. Okay, that part was clear.
Okay. Is it clear now?
Yes.
Okay. Okay. So, hmm. So let's move on to the next one. Let me quickly have some water. Okay. So what is the problem saying? That we have a product of position vector xy in terms of spherical rank 2 tensor will be. So okay, so notice that this is rank 2 tensor. So in the previous problem where we used these values, right? So this was a rank 1 tensor, right? Because it only had z, y, so here it was 1, 1, so on. Now because it's a product of x, y, so naturally it will be a rank 2 tensor. And then we have to write what will this product xy be in terms of this tm tensors basically. So what do we know about these tms? So one equation that we know, that this t plus 2, that this is given as 1 by 2 x squared minus y squared plus 2 iota xy. And another of this, when m is minus 2, is given as x squared minus y squared minus of 2 iota xy, right? And the question asks us to find out xy. Okay, so from just by looking at these two equations, we can see that if we subtract them, then these terms will cancel out and these terms will add, right? So we'll only have some xy terms remaining on this side. So let's do a subtraction. So upon subtracting, we'll have t plus 2 minus t minus 2. So this will be half of x squared minus y squared plus 2 iota xy, and then minus x squared minus y squared, sorry, this will be plus y squared and plus 2 iota xy, right? So this will cancel out and this will cancel out and we'll have 4 iota xy, right? And then if we divide that by 2, so this will be 2 iota xy. Therefore we can write xy as t plus minus t minus 2 divided by 2 iota, right? Or if I want to take this iota on top, I can do minus iota, right? So minus iota by 2, so which is option A. Hmm. Okay, any doubts?
No, sir.
Okay, good. So then let's move on to the next one. So again, we have one more problem which is related to the addition of angular momentum. Okay, and the question asks that what will be the maximum degeneracy of states when we add angular momenta J1 and J2. Okay, maximum degeneracy. So the question is asking about the maximum degeneracy. We are given J1 as 4 and J2 as 2. Okay, so what is degeneracy? So degeneracy is number of ways to obtain specific m which is nothing but m1 plus m2, right? That is the degeneracy. Now for J1, because J1 is 4, so what is the possible values of m1? So m1 varies from -4 to +4, and m2 varies from -2 to +2. Okay, so what will be the range of total m? So our m will go from hmm, okay, so our m can go maximum up to 6, right? So we can have uh, several possibilities here, right? So it is always good to check for m, the total m is equals to 0 state, because that generally has the maximum degeneracy. So how will we get 0? So m1 is -2, m2 is +2, and then -1 +1, 0 0, +1 -1, +2 -2, right? So for the 0 state, what do we see? We see that we have covered all possible values of m2, right? We have covered all possible values of m2, and the degeneracy is coming out to be, so degeneracy is 5. So the answer is 5. Okay. Had we taken some other state, let's say for example we could have taken m is equals to 2 state. Okay. Then for m2 as +2, we would have m1 as 0, and then +1 +1, and then for 0 it has to be +2, for -1 it had to be +3, and for -2 it had to be +4, right? So again, because we are using all values, so degeneracy will be 5, right? But if we go one step higher than 2, for total m is equals to 3, then we'll start having some problems, right? Because for this minus, when this m2 is -2, we will require m1 to be, sorry, m2 is -2, we'll require m1 to be 5, which is not possible, right? So this is not possible. So the degeneracy will only be 4. Yeah. So maximum degeneracy is when we have all 5 covered. So that is generally true for 0 state. Now, based on all this discussion that we have just had, okay, so all this thing, what do we realize? That for the smaller of the two, so here for example this is smaller, then we can say that our degeneracy, so our degeneracy will cover all possible states of the smaller j, right? So here smaller j is 2, and therefore the it's coming out to be 5. So what is the formula? 2j, I'm writing smaller, plus 1. Okay. Why? Because our total values of m goes from -j to +j, right? So -j plus 1, so on, and then here we have 0, and then here we have j minus 1 and j. So these are total 2j plus 1 values, right? 2j plus 1. That's why we have this formula for degeneracy. Okay. So let's say if I now ask you that if you are given two states instead of 4 and 2, if we are given two states, let's say 5 and 1, then what will be the maximum degeneracy? So the maximum degeneracy will be how much?
3.
3. Yes, exactly. And if instead of 1 we have, let's say, 3, then maximum degeneracy will be
7.
7. Exactly. Okay. So this is how we find out the maximum degeneracy. Okay, so for this case the answer is 5. Let's move on to the sixth problem. Right, so we are given a state vector, which is this thing, and so first of all, is it normalized?
Yes.
Yes, it is normalized, because this will give us 1 squared, and this will give us 3 squared. If we add them, we will get 10. So this root 10 and this root 10 will cancel out, right? Okay, so this is in fact normalized. Yeah, so the possible measurements of square of angular momentum L square on the eigenstate, this thing, is how much? So this is the problem. So the question is that if we do measurement of square of angular momentum L square on the eigenstate 2 minus 1, then what is the answer that we will get? So we know that for L square operating on, yes,
L into L plus 1. Is it like that?
yes, so L square operating on a state L comma m, it gives us L plus 1 as the eigenvalue, and the eigenstate remains the same, right? So for the eigenstate 2 comma 1, L is 2, right? So this eigenvalue L, okay, sorry, there is one h cut square also, right? So this eigenvalue will be L plus 1 h cut square, so 2 plus 1 h cut squared. So this is just 6 h cut squared. Now is this the final answer, or should we consider this 1 by root 10 factor? What do you think?
I think this is the final answer.
Sorry?
This should be the final answer.
It should be final answer. Yes, it is the final answer. Because it is the final answer because we are operating L square on this eigenstate. The problem does not say that operator L square is operating on psi. Right? It does not say that it is operating on psi. It is just operating on this eigenstate. Okay, so this is the final answer. Right. Okay, so one very similar problem we solved in the last tutorial. Let's see if we can use our previous knowledge to solve this problem. Again, we are given two atoms and two angular momentum. So one atom has angular momentum 2 and the second atom has angular momentum 1. So they are coupled, so we have to add them and described by the Hamiltonian. So this is the Hamiltonian. H as epsilon j1 dot j2. Okay. where epsilon greater than 0. If the Hamiltonian acts on j comma m state, then the energy eigenvalues corresponding to the possible values of total angular momentum j will be. Okay, so what do we need to find? We need to find the energy eigenvalues, right? The energy eigenvalues. This is what we are supposed to find. So what is the first thing that comes to your mind when we want to solve such problems? Like what should be the first thing that we need to do? Okay, so first of all, we should recognize that what this Hamiltonian is acting on. So it is acting on this j comma m state. Okay, our Hamiltonian is acting on this j comma m state. So this is our basis states, right? And what defines these basis states? So these are defined by jz or j square, these kind of things. Correct? Right? So basically, this j1 is not an eigen, is not an sorry, is not an, will not give us an eigenvalue. So this j comma m state is not an eigenket of j1. But if we have j1 square, then this is written in the basis of j1 square and jz. So as we had done also in the previous, in the one of our previous tutorials, we need to change this j1 j2 to j square and jz or these kind of things, which will give us some eigenvalue, right? Which spans this eigenket, right? Okay, so how can we convert this j1 dot j2 to some j square kind of a thing? For that, we need to expand this j1 plus j2 squared, right? So j squared we can write as j1 plus j2 squared, right? So this means this we can write as j1 squared plus j2 squared plus 2 j1 j2, j1 dot j2, right? So our j1 dot j2 then becomes half of j squared minus j1 squared minus j2 squared. Therefore our Hamiltonian h becomes epsilon by 2 j squared minus j1 squared minus j2 squared. Now using our Schrodinger's equation, h psi is equals to E psi, so our energy eigenvalues will be epsilon by 2, and when this j square will act on our state, this j comma m states, what will we get? We will get j plus 1, and this will give us j1 plus 1, and this will give us j2 plus 1, and one h cut square coming from all of these terms. Okay, now what is, so j1 is 2, right, and j2 is 1, so our total j will be 3, right? And okay, not 3, okay, so when we add these, so again we use triangle inequality, so our mod j1 minus j2 less than equals j less than equal to j1 plus j2. So this implies that our j will have three values, 1, 2, 3, right? J will have these three values. Okay, so let's start with the highest value, 3. Okay, for j as 3, our energy will be epsilon h cut squared over 2, and so this will be 3 times 4 is 12 minus, okay, so j1 and j2 they are fixed, right? So it is 2 and 1. So this quantity is always 2, 2 plus 1, and 1, 1 plus 1. So this is 2 times 3 is 6, and this is 1 times 2 is 2, right? So it is always 6 and 2. So this will give us 12 minus 8, which is 4, and this cancel out. So 2 epsilon h cut square, right? Similarly, for j is equals to 2, our energy will be, now instead of 12 we will have 2 times 3, which is 6. So 6 minus 6 minus 2, right? So they will cancel, and this 2 will cancel. So simply minus epsilon h cut squared. And for j as 1, our energy will be so 1 is 1 times 2, so this is 2 minus 6 minus 2, and this minus 6 by 2 is minus 3. So minus 3 epsilon h cut squared. Yes, so minus 3 minus 1 and 2. So minus 3 minus 1 and 2. So option A. Any doubts in this one? Do you want me to quickly go over it again? Just to recap.
Not clear.
Sorry?
Clear. Okay.
Okay,
It's
it's
fine.
okay. Okay, so then let's take a small break, and then we'll look at this problem. Okay, just give me 1 minute.
Just a moment, sir. Could you go back to
Yeah,
the previous question
sure.
once?
Yes.
Okay.
Okay, so let us resume. This problem is regarding the selection rules, right? So we are given a Clebsch-Gordon coefficient. It is given as m1 is j1 minus 1, m2 is minus j2 plus 3, and then j is j1 plus j2, and we have m. So for it to be non-zero, the question asks it will be non-zero. So what is our what will be our selection rule here? So the selection rule will be that this m is equals to m1 plus m2. Okay, so this means that our m will be j1 minus 1 plus minus j2 plus 3. So this is j1 minus j2, and minus 1 plus 3 is plus 2. So option C. Okay. Okay. Okay, so moving on. So parity operator. So the statement is that this parity operator P anti-commutes with orbital angular momentum L. Is this statement true or false? Till now we have solved a lot of such problems regarding the parity operator. So what do you think? True? False? You can take a guess.
Uh, since L is a vector quantity, so the parity operator should change the sign of L.
Okay. So let's rewind. So we know that P will change R to minus R, right?
Mm,
This is what P does.
yeah,
Now, how can we write our angular momentum? So, as you said, it is a vector. So, in terms of R, we can write this like this: R cross P. Now, what happens to R? We already know that it changes to minus R. And what happens to P? Will it remain same, or will it change this? Will it change its sign?
I think it remains same because last time I said that the velocity doesn't change.
Oh, that was, I think you are confusing between time reversal operator and parity.
Okay, okay. So,
Yeah. So, P we can also write as m dr by dt, correct? And so m will not change sign, t will not change sign, but you can see this r will change sign, right? So this also goes to minus p, correct? Therefore, so our total angular momentum L will not change sign. So this minus minus will become plus, so it remains as it is. So therefore, this parity operator P, if we write this equation, P L P inverse, it remains L, right? So this thing. Now we can we can operate P from right hand side to both equations, right? The standard thing that we do. We'll get this, right? And then we can rearrange. So we'll get PL minus LP is 0, or p comma l is 0. So they commute, right? And the question says that they anti-commute. So this statement will be false. Okay. So
One thing,
yes, ma'am.
if L is the vector product of R and T,
Yeah.
so if both are changing sign, then by cyclic rule, will it remain plus or will it become minus?
Now because both are changing sign, so this r becomes minus r and p becomes minus p. So this again becomes r cross p, which is nothing but L again, right? So since you brought it up, let's also check instead of parity operator, if we have time reversal operator, then will it commute or not? We can check. Okay, so let's say instead of parity operator P, we are now considering the time reversal T. So what will happen under time reversal?
R will become minus R and P will remain P. So L
Uh,
will become
no, again. So for time reversal, as we discussed, it's easiest to imagine that something is traveling and we record and then we rewind, right? Right? So this is going like this. So what we'll see that now it is going like this. So under time reversal, r does not change its sign. Instead, the velocity changes its sign. Okay? Or we can say the momentum instead of velocity, because momentum is just mass times velocity. So momentum will change its sign. So this is what happens in time reversal. Therefore, because only one of the quantity of these things is changing sign p, so this becomes r cross minus p, and so this becomes minus L. So our L transforms like this, right? It goes to minus L. Therefore, if I now write this equation, T L T inverse, I am getting minus L. And now again I can operate on right side with T. So I'll get this, and then I can write it like this. So this is actually anti-commuting, right? So T comma L is 0. Is this clear?
yeah.
Okay. So the time reversal operator anti-commutes and the parity operator commutes with our angular momentum operator L. Okay. So question 10. What are we given? That a beam of particles is subject to a simultaneous measurements of angular momentum variables L square and Lz. So what are we doing? We are measuring simultaneously. Okay, simultaneous measurements. The measurement gives pairs of values. L is equals to m is equals to 0 and L is 1, m is minus 1 with probabilities 3 by 4 and 1 by 4 respectively. The state of the beam immediately before the measurement can be written as. Okay, so generally we write our state like this, correct? So this L equal to m equal to 0 will corresponds to this state, and L is equals to 1, m is equals to minus 1 will correspond to this state. Now the probability was 3 by 4 here and 1 by 4 here. So what will be our total state psi out of all these given options? Which one do you think is the right one?
C, inside.
Sorry?
Can you show the full question?
Yeah, sorry.
Using another factor also, no, to follow. Is
Yes.
the alpha.
So there is one factor which is coming. You are right. So first of all, what we can do, can we eliminate some options? Like for example, option B and D have coefficients 3 by 4, 1 by 4, and options A and C have under root 3 by 2 and 1 by 2. So which should be the form?
The A of C.
A or C, right? So let's eliminate B or D.
Hmm.
Now, what is the difference between A and C? That we have this e to the iota alpha factor coming in one case with the second state and in one case with the first state. So which option should be correct?
First,
Why first?
we got when L and M are 0, 0,
Mm-hmm.
that can be taken as phase alpha 0 with respect to the 0, 0.
Mm-hmm.
We can have some phase in the other 1 minus 1.
Yeah, exactly. So the answer will be A. Okay, so good.
I couldn't hear mom's explanation. What did she say?
Ma'am, can you please repeat?
Yeah, I said that the 0, 0, if I compare 0, 0 with the state 1 minus 1, then if I take 0, 0 as the base state, then that angle alpha can be considered with the other state, which is 1 minus.
Yes.
Although alpha is arbitrary, it could be
Yes.
plus, could be minus, and so it could be with either. It could be with either.
Yes. Yeah, you are correct. So we option C is also, we can also choose option C. Doesn't matter. It will not change the results of the experiments which is defined. Right? We will still get same probabilities 3 by 4 and 1 by 4. Yeah. But conventionally, the state with higher M is generally referred as the, as a reference, and compared to the higher M, we assign a phase to a lower M. So that is convention. So if for example this was a multiple select question, both A and C are correct. If you just have to choose one option, if it is just a multiple choice problem with one option correct, then we generally assign phase with the lower value of M. That is like the convention.
But what about if in the question it is given m is equal to 1 and m is equal to 1? Then that means this alpha would have been with 0, 0 t. Is it?
What was the modifications you told?
The first is the same, L is equal to m is equal to 0. The
Hmm.
second state is n is equal to 1 is
Okay.
equal to m.
M is equals to
1.
1. Okay. Then option C would be preferred.
Okay.
Yes. But like in both the cases, as you said, the results of the experiments will not change, right? The measurements, the probabilities, they'll remain the same. Yeah, it's just like more like a convention kind of a thing.
Mm-hmm.
Otherwise, it's the same. Both A and C are telling us the same thing.
Yeah.
Sir, over
Yes.
here, uh,
Sorry.
I did not understand the answer, how we got the answer. Because when mom was speaking also, sorry, it was my problem, but she wasn't audible to me.
Okay. So let me explain to you again. Okay. So there was some measurement conducted and we had two possible states, right? We only obtained these two pairs, that L and M both are 0, right? So this state, right, 0 0 state, and L is 1, M is minus 1, so this state 1 minus 1 state. The corresponding probabilities are minus 1 by 4 and 3 by 4. These are the corresponding probabilities. So for it to be 3 by 4, the coefficient of this thing, we know what will be the coefficient. It will be the square root of this thing, so under root 3 by 2. And the coefficient of this thing will be the square root, so 1 by 2. Right, so now if you look at the options, so clearly we can eliminate B and D. Right, now in option A, we have this phase e to the iota alpha. So this phase is with the second state, and for option C, this phase is with the first state, so the 0 0 state. Right, so you can see we have e to the iota alpha here and e to the iota alpha here. So what we were discussing, that if this was a multiple select problem, because this e to the iota alpha will not affect your probabilities, right? Your these probabilities 3 by 4 and 1 by 4 will remain same no matter what is where you take your e to the power iota alpha. So both options are correct. But if you only have to choose one, so generally like we have this convention that we associate this phase with lower m. Okay, so lower value of m. So in this case, you can see the lower value of m is minus 1, right? Minus 1, which is the second state here. That's why we have multiplied this phase here. So what ma'am was saying, that if instead of L of instead of this state 1 minus 1, we were given a state 1 comma 1. Then because now this m is higher than 0, so then option C would be a preferred choice. That's it. That is what we were discussing. Okay.
Yes.
Okay. So now, yeah. So now I wanted to have this small kind of tutorial where we'll see how we can calculate Clebsch-Gordon coefficients using the ladder operator methods. Okay. Okay. So, and we will consider two spin half particles. We'll consider two spin half particles, and what we'll do, we'll find out the Clebsch-Gordon coefficients. Okay, so because we have two spin half particles, let's say two electrons, okay, let's consider two electrons. Each with spin S1 as 1 by 2 and S2 as 1 by 2. Okay, so we'll be just talking about the spin angular momentum. So what we do, we will find total angular momentum states and we write them as capital S, comma capital M in terms of S1 M1 and S2 M2. Okay, so essentially we now have two things. So firstly we have two electrons and they are having their own spin S and their own spin magnetic number M. right? But then when we add them, so the total values s comma m, we want to find out that how they are related with each other. Okay, so to tell you what I'm talking about, hmm. So here we have s1 as 1 by 2 and s2 is 1 by 2. So what will be my m1 and m2? So my maximum m1 can be 1 by 2 and minimum m1 can be minus 1 by 2. So for this I can have two values of m1, which is minus 1 by 2 and 1 by 2. Similarly, I can have two values of m2, minus 1 by 2 and 1 by 2. So this is clear, right? This is very, like, we have covered this multiple times. So now if I add them, we know how to add, right? We will use our triangle inequality. So s1 minus s2 mod, it will be less than our total s, which will be less than our s1 plus s2. So what will this give us? So s1 minus s2 will be 0 and s1 plus s2 will be 1. So our s also has now two possible values, 0 and 1. Okay, so when s is 0, my m will be 0, and when s is 1, my m will have three values, minus 1, 0, 1. Okay, and this is the famous singlet triplet states, right? So this is the singlet and this is the triplet. Okay, so this is the addition of angular momentum. Okay, so on my left hand side is our individual spins, and on the right side is the spins of two electrons when we have added them. So upon adding, we get these possible values of s and m, and before adding, we have this for first electron and this for the second electron.
One thing, when we say we are adding
Yes,
the two electrons, does it mean that the two electrons are now coupled?
yes,
Uh,
yes,
this is
exactly. Yes, so we are now considering, so this, okay, let me write. So this is the coupled state. So when they are coupled, we have to add their angular momenta, and this is how the angular momentum are added. Yes. Anything else before we move on?
Ma'am is mentioned reducible and irreducible states also.
Irreducible and irreducible.
States also. The
Sorry.
coupled ones are, I forgot, coupled and uncoupled, and reducible and irreducible. I can't recall. Maybe Harsul will be able to tell. Harsul, do you recall?
I
Sorry, Manu. Did you ask something?
Yeah,
Reducible
ma'am is
and
asking, do you recall anything taught in the lectures regarding some coupled, uncoupled states and something which is reducible and irreducible?
Uh, no, I mean, I don't recall anything.
okay, okay. Okay, it's fine.
Okay. So now the thing is, on my left hand side is uncoupled state, right? So this is uncoupled, and on right side is coupled state. So now what mm, like physically we have seen like how these are adding and all, but mathematically how we can write our coupled state in terms of our uncoupled state is given by Clebsch-Gordon coefficients. Okay, that is where this requirement comes from. So yeah, so the, okay, let's first write the uncoupled basis. Okay, let's define the notation. So for the uncoupled basis, we can have, let me write up spin for m as plus 1 by 2 and down spin for m as minus 1 by 2. Okay, and because we have two particles, so therefore we can have total 4 possible states, right? What will be these 4 states? So one will be up up when both electrons have up spin, then up down, and then down up, and finally down down. Okay, so here m1 is half, m2 is half, m1 is half, m2 is minus half, m1 is minus half, m2 is plus half, and here both are minus half. Okay, so this is our uncoupled states. And what will be our, okay, so I'll just get rid of this thing. So for our coupled state, we will follow the notation, this notation, right? S comma m, we'll follow this notation. So this, let me just write S and M. Okay, so then for the coupled state, we'll have these 4 possible states, right? So let's say I'll write the singlet first, 0 0, and then 1 minus 1, 1 0, 1 1. Okay, is this okay? Let me write it here. Now because they are spanned by the same basis, okay, they are spanned by the same basis, so then mathematically it should be possible to write them in terms of these states. So let's say I have alpha, so alpha 1 up up plus alpha 2 up down plus alpha 3 down up plus alpha 4 down down. Okay, so I can do the same thing for the remaining, and instead of alpha let me write beta. So this up up, beta 2 up down, beta 3 down up, and beta 4 down down, and then I'll have gamma 1 gamma 2, sorry, gamma 1 gamma 2 gamma 3 gamma 4, and let me write down delta, delta 1 delta 2 delta 3 delta 4, and then these same states up up, up down, and then down up, and down up. Okay, so these alpha beta gamma delta, these are my Clebsch Gordon coefficients. So you can see that these Clebsch Gordon coefficients, what they are doing, they are mathematically connecting my coupled states to my uncoupled states. Okay, that is the function that they are solving. Now, straight away, so okay, so here you can see that my total m is 1, right? So for this state, what we notice straight away, that my m is 1. And what is my m? My m is m1 plus m2. So both of them have to be plus half to give me a one state, right? Which means that my up state directly corresponds to my m is equals to 1 state directly. Okay, and which means that these three, delta 2, delta 3, delta 4, they'll be 0. Okay, so delta 2 will be 0, delta 3 will be 0, and delta 4 will be 0.
Sir, over here, I did not get this intuition. You-
Okay, so for this state, okay, this state, so this, what is this? Okay, so if you follow this convention and you compare, so for this state, my m is 1, right? Correct. What will be the total m that you will get for this case? So here one is plus half, one is minus half. So your total m for this case will be 0. Again, similarly, for this case also it will be 0. For this case it will be minus 1, and this case it will be plus 1, right? So because my total m is 0, I cannot have any, sorry, my total m is 1, I cannot have any terms that will give me m is 0, 0 or minus 1. Okay. Did you understand it now? So I am expanding. Okay, let me try again. I am expanding my 1 comma 1 state in all these 4 possible states. Let's say one of them is non-zero. Let's say this delta 2 is non-zero. Okay, so then my 1 comma 1 state, let's say I can normalize and write this like this: up and plus 1 by root 2 sum up down, like this. Now on left hand side, I always have total angular momentum, this m as 1, right? You can see it's always 1. But on right hand side, although this term is giving me 1, but this term is giving me 0. So this is not possible, right?
Yes,
Yes. Another way to think about it is our selection rule. Yes. So what was our selection rule? That m1 plus m2 has to be equals to m. This is our selection rule, and it comes from the same intuition, right? So here our m is 1, so only possibilities, okay, our m1 can have either plus half or minus half. So only possibility for this selection rule to be followed is when both of them are plus half, correct? Which means only the first term. All other terms, they do not follow this selection rule, so they are essentially 0. Is it clear now?
yes,
Okay. Now following the same logic we have done for m is equals to 1, we can do same for m is equals to minus 1. So here we have m is equals to minus 1. Now tell me, beta 1, beta 2, beta 3, beta 4, which term will remain? 3 will go to 0, right? Which term will remain?
Okay, to be honest,
both the down arrows down.
Yes, so beta 4.
the
So this will go to 0, this will go to 0, this will go to 0, and beta 4 will remain. Is that correct?
Yeah.
Yeah, because they follow the selection rule. Minus half gives me -1, and that is matching here. So selection rule is followed. Now let's come to this 0 terms, right? So let's start with the third one first. Let's finish our triplet state. So here 0. So 0, you can see it's coming from these two states, right? Up, down, or down, up. So by
Down.
selection rule, we can eliminate two terms, right?
Hmm.
Which two terms can we eliminate?
Gamma 1 and gamma 4.
Gamma 1 and gamma 4. So this is 0 and this is 0. Oh no, sorry. Gamma 4. So gamma 1 is 0 and gamma 4 is 0. Similarly, for our singlet state, alpha 1 will be 0 and alpha 4 will be 0. So we started with 16 elements and we have now reduced them to 6. Okay. So we have already eliminated 10 elements. So now, okay, let me erase this thing. Now we'll start assigning values of this delta, alpha, beta, gamma, delta. So let's start with this last state, 1, 1 state. So we are writing this state 1, 1 as delta 1 up, up. Now straight away, using normalization condition, right? Because this state has to be normalized. What do you think will be the value of delta 1?
1.
1. So this is simply 1. Okay. So from this, like whenever we have any given states, whenever we want to find out the Clebsch-Gordon coefficients, just remember that the value with your highest weight, right? So here we have S is maximum, right? S is maximum and M is also maximum. So this is the state with the highest weight. So its Clebsch-Gordon coefficient is always 1, right? Because there is only one possible way of representing it. So this is a very simple example, but no matter if even if you take a complex example, then also you'll realize that there is only one possibility of attaining that maximum weight, right? So this the Clebsch-Gordon coefficient of the maximum weight is always 1. So for example, today we solved one problem, right? Where we had problem 3. Yeah, here. So here you can see that in this problem, the Clebsch-Gordon coefficient will be 1, right? Because you can see that this is the maximum state. 3, 3 is the maximum state. We cannot go above that, right? So our 3, which corresponds to our, so here if you go back F. So here, what is the maximum value of L that we can have? Because the maximum is F orbital. So maximum L is 3, right? Maximum L is 3, and correspondingly maximum L will be 3. So the 3, 3 state will be the maximum weight state. So directly when I was asked about the Clebsch-Gordon coefficient, I know that it is going to be 1.
Okay.
Okay, so we have already used it before, but I didn't explain much why it will be 1.
Mm-hmm.
And by selection rule, this Clebsch-Gordon coefficient, we could say that it is going to be 0. Okay, so two of them are already used, what we just discussed. Okay, let's go back. Yeah, so we were here. So basically this thing, it just tells us that for maximum weight, our Clebsch-Gordon coefficient is 1. Great. Now for the 0 state, again I can write, no, not 0 but 1 minus 1, sorry, the 1 minus 1 state, right? This is the minimum wait state. So again here it was beta 4 down down. So again just by normalization we will get beta 4 is equals to 1, right? So this is our minimum weight. Again there is only one way to get the minimum weight, so following the same logic, the minimum weight is all the Clebsch coefficient of the minimum weight is always 1. Okay, so delta and beta are done. Now let's look at alpha and gamma. So for the for the m is equals to, basically we are now left with m is equals to 0 states. Okay, so let's go to the next page. So m is equals to 0 states. So whenever, okay, so we have already found out the highest weight, right? The highest weight. Now what we can do to find out the subsequent Clebsch Gordon coefficients, what we will do, we will apply the lowering operator. Okay, so apply lowering operator on both sides. So my s minus, so this s is total, and I'll write s1 minus plus s2 minus. So on left hand side I'll apply s minus, on right hand side I'll apply this thing. Okay, and for any lowering operator in general, right, if I have some lowering operator j minus acting on state j comma m, what does it do? It does this thing, h cut j j plus 1 minus m m minus 1 j comma m minus 1. So this is what it does. Fine, this is what it does. So now we have this equation already, right? The 1 1 and this up up configuration. So now we'll lower this, right? So this will become 1 0, right? If I apply the lowering on 1 1, you can see it will become 1 0. So let me apply the s minus on 1 1. So s minus on 1 comma 1 will give me h cut. Non comparing, my j will be here 1 and 1 plus 1 minus m will be 1 and 1 minus 1, and this will be 1 comma 0. Okay, so this will be 1 plus 1 is 2 and this
In
is
this
0.
shall we take half instead of j, it is s, na? S given is spin half.
Yes, yes.
So shall we take half and half
Mm,
plus 1 or no?
so yeah, you are right. So we'll take half when we are doing on the right hand side here. Now we are doing it for the this thing. Now we are doing it for the coupled state. Let me write. Maybe then it will be clear. So right now I am doing coupled state. Okay, and specifically coupled state considering s is 1 and m is 1. Okay, so this
Okay.
last state, the highest weight state, this
Mm,
state.
mm.
Okay, so my s is 1, m is 1, right, for the coupled state. So this will be just root 2, right? So this will be under root 2 h cut 1 comma 0. Okay, now now I'll do this on the uncoupled state. So let me write uncoupled. Okay, so for the uncoupled state, s1 minus plus s2 minus, and this will operate on the up up spin, right? Because this up up spin corresponds to my 1 1, right? basically this equation. Here delta 1 is 1, and
Okay.
then I have on this equation I am operating this thing s minus on the left side and s1 minus plus s2 minus on the right side. Okay,
Mm.
so I'll get this thing, and then finally I'll set both of them to be equal because they are equal. Okay, so this will give me two terms, correct? So s1 minus will act only on the first spin, right? So what will I have? So this will give me h cut and under root. Okay, so
Then
okay,
S1 minus
yes,
will operate on first arrow and S2 minus will operate on second arrow. Is it like that?
yes. So let me first write it like this. So s1 minus will operate on the first arrow, okay, and then I'll have the second arrow, which is not bothered by s1, and then I'll have first arrow which is not bothered, and then I'll have s2 minus and this thing, so that it is more clear to us what we are doing.
Mm.
Okay, the order of operations. So now this first term h cut under root. So now this up spin, if you so for this up spin, my s is half, my m is half, correct?
Mm. Yeah.
Now I'll plug this in this thing, so I'll have half plus 1 minus half, and then half minus 1 is minus half, right? So this thing. Okay, so and then what it will do, so because it is a lowering operator, right? So it changes m to m minus 1, so j will remain same, so it will go to, so its final state will be s as half and m will be minus half, so it will become a downspin, right? So here I'll have a downspin, correct? And this spin remains as it is, so this spin remains upspin. Okay,
Mhm.
is this clear?
Yeah.
Yeah.
Sir, I did not understand this part in uncoupled state when you split these two things. The two up arrows were split into two single states, two up arrows. S1,
Okay, okay, this state, this line, this one.
yes,
Okay, so when we write, let me let me take my pen. Okay, so when we write this state, right, up state, because this is uncoupled state, right? This is uncoupled state. They are not interacting with each other, right? So it is simply this first electron and then second electron. That's it. Because they are uncoupled, right? So we can just simply multiply their wave functions. They are uncoupled. Okay? And so this first one will correspond to our first electron, and the second one will correspond to our second electron. And when I do S1 minus on this thing, so this operator corresponds to my lowering of the first electron. So it will affect only my first term, and second term remains as it is. So this S1 minus will act on my first electron, and my second electron remains as it is. If I do S2 minus on this same state, so this time my first electron will remain unchanged, and my second electron will feel this lowering operator. Okay, so that is what we have written here. And just add these two, and this is what we will get. Is this clear now?
yes.
Okay. Okay, right. So then first term is giving this, and second term h cut. So this thing will be same, right? Because again we are doing same operation on up spin, so we'll get same half, half plus 1, minus half, and the only difference will be this first spin will be up and second will be down. Okay, and this is 1 by 2 plus 1 is 3 by 2, 3 by 4 plus 1 by 4, so this is just 1. So we can write this in total as h cut common down up plus up down. Okay, and what did we get here? We get this thing. So from the coupled state we got under root 2 h cut 1 0. So under root 2 h cut 1 0 is this. So let's cancel out these h cuts. We can cancel out h cut, and let's take this under root 2 to this side. So this will be 1 by root. Okay. So this is what we get. So now if we compare back here, this is the state, right? 1 0 state. So the 1 0 state we have successfully written in terms of up down and down up, and these coefficients are coming out as 1 by root 2, 1 by root 2. Okay, so my 1 0 state, which was gamma 2 up down plus gamma 3 down up, we see that gamma 2 and gamma 3 both are equal, and it is coming out to be minus, sorry, plus, it is coming out to be 1 by root 2, and you can see that this is also normalized, right? Okay, yes. So now we are left only with our singlet state. What was our singlet state? The singlet state was 0 1, and again it was written in terms of these two same states, up down and down up, these two states, and the coefficients were alpha. So alpha 2 plus alpha 3, these two states.
Wasn't it 0 0?
Yes, sorry. This will be 0 0. Sorry. Okay. So, so in the beginning we had 16 CG coefficients. By selection rule, we got them down to 6, and we have already found 4. Only 2 are remaining. And one thing that we can notice, so this is very common. You will come across this thing. So for this last one that is remaining, you can see it is formed of the same basis states, right? So up down down up, here also up down down up. Only the coefficients have to be different. So one trick that we always use is the orthogonality. Okay, we know that these two states, they'll be orthogonal to each other. Okay, and by orthogonality, what will happen, that if we do this operation, basically 0 0 1 0, we should get 0. Okay, so by orthogonality, and okay, let me write 1 0 0 0, this has to be 0. Okay, this has to be 0. Now 0 0 we have already written, sorry, 1 0 we have already written as 1 by root 2, 1 by root 2. Okay, so this is already 1 by root 2, uh, the up down plus 1 by root 2 hmm, down up. Okay, this is my 1 0 state, and my 0 0 is alpha, what, alpha 2 alpha 3, yeah, alpha 2 alpha 3. So alpha 2 for the up down state, alpha 2 for my up down state, and plus alpha 3 for my down up state. Okay, so this should be 0. Okay, this should be 0. Now, so this will will be this, so it will give me alpha 2 by root 2, and it will be with this, so this will give me plus alpha 3 by root 2 is 0. So which implies alpha 2 is equals to minus alpha 3. And now also we have the normalization condition, which gives me that alpha 2 squared plus alpha 3 squared must be 1. Okay, so now let me put this alpha 2 as minus alpha 3, so this becomes alpha 3 squared plus alpha 3 squared as 1 minus alpha 3. Okay, so this gives me 2 alpha 3 squared as 1, or alpha 3 as 1 by root 2. So my alpha 2 is then minus 1 by root 2. Okay, so this implies that alpha 2 equals to minus alpha 3 is equals to 1 by root 2. Okay, so using orthogonality we could also find out our last two remaining Clebsch-Gordon coefficients. Okay, so I hope now it is clear that how we find out the Clebsch-Gordon coefficients. So we start with the highest weight, and then we keep on applying the lowering operator. Okay, for this case we just have to apply it once, but let's say if you have more and more states, then we just keep on applying the lowering operators, right, to get to the lower values of m. And finally we use the orthogonality relation and normalization to get the last remaining Clebsch-Gordon coefficients. Okay, I guess it's already time.
Do we have to write it in the matrix form also? Like
Yes,
for,
yes, then
for
we
matrix?
can. Okay,
Huh?
so here you can see it's like a matrix only,
Yeah.
right? This is just like a matrix only, and then we can write this down in the matrix form. So these two you can see will be 1 by root 2 and minus 1 by root 2. This will be 0 there, and then we can write it down. Do you want me to write it down?
Yeah, yeah, yeah.
Okay.
The left hand side and the right side.
Okay. So let me write it down this way. So it will be 1 1, 1 minus 1, 1 0, and 0 0. 1 1. So 1 1, 1 0, 0 0, and 1 minus 1. Okay, and then I'll have my coefficients here, and then so it will be 1 1, so we'll have up up, and then finally we'll have down down. So here I'll have up up, and then let me write up down, down up, and down down. Okay, so this will be 1 0 0 0, right?
Mm-hmm.
So and for this last one, 1 minus 1, I know this will be 0 and this is 1. For my 1 0, so for 1 0 it is 1 by root 2 and 1 by root 2 for this both of them. So this will be 0 0, 1 by root 2, 1 by root 2. Okay, and then again for this also it is 0, 1 by root 2 and minus 1 by root 2 and 0, like this. So these are my coefficients.
Thank you.
Okay. Okay then, I hope this was useful, and then I'll see you next Saturday. Have a
Thank you.
good night. Bye bye.
Thank you. Bye. Thank you so much.
Yeah.
Bye.
Bye bye.